Swayam Prabha. Digital India. Educated India.
All of these examples we saw now, the TSP graph coloring used dynamic programming. Okay. So, recall the set cover problem. You have a universe which without loss of generality we will assume it to be this, and I have a family of sets and each SI is a subset of X. This is my input, and the output I am interested in a subfamily of my family. So, a collection of some small number of sets such that union f prime, f in f prime is my entire universe set, and we saw greedy algorithm does not give you optimum, it gives you some log n times optimum at most, but now I want to find the exact optimum, right. We are looking at exact algorithm. What would be a brute force algorithm here? All subsets of f, because naturally whatever you are looking for output will tell you, guide you how to do, right. You try all possible subsets, subfamilies of f, see whether the union is M, the universe, and among all of such subsets pick the one which has the minimum subset, and the running time would be how much? 2 power m, because m is the size of the family, right. 2 power m times n or something. This is to check whether the union of your sets in the family is the universe. But m could be very, very large, right. M is subsets of the universe. So, that could be as bad as 2 power n. I might have all possible subsets here. So, I do not want my algorithm's running time to depend on m, I would rather have it depend on n. Okay. So, we will design such an algorithm using dynamic programming. So, how do we set up dynamic programming? We want to check what are the sub problems to compute, and we will look at the optimum solution that will tell us what are the sub problems to compute, right. So, okay, so I have my universe and my family contains S1, S2, some Sm. So, we will try and detect some optimum substructure property. Actually, I think we probably did something similar for knapsack or some such thing. Okay. So, if Sm is in my final optimum solution. Okay. So, the final Sm may or may not be in my optimum solution. If it contains the optimum solution, if it is in the optimum solution, then can you tell me what about the remaining? What are they trying to do? What is the optimum substructure there? Then I claim what about f prime minus Sm is an optimum solution for what universe, what family?
X minus Sm.
And f minus Sm, right. Sm is covering some set of elements. So, I remove it from my set universe and I go to the remaining thing. I want my remaining family to cover the remaining sets optimally, right, clearly. So, in my f prime, the remaining sets is the optimum number of sets that cover the remaining universe from S1 to Sm minus 1. If Sm is not there, then f prime itself is the optimum solution for what? X comma f minus Sm, because if Sm is not there, then 1 to m minus 1 itself are covering x, and this must be the optimum solution, because if they, so this is the optimum substructure property. If there is a better solution, then you would have picked that in your overall optimum solution also. Okay, that is a kind of argument. So, this suggests the sub problems, this suggests the recursive formulation, right. So, the sub problems would be, so my opt, so in general, so what are the sub problems? The sub problems is either 1 to m or 1 to some I or 1 to m minus 1, and I want to cover some subset, opt some subset, because I do not know what Sm contains. Well, I know, but I have to, I am going to, Sm may or may not be there, and as you progress you might have picked a bunch of sets. So, what is this remaining set to be covered, you do not know, because it is a choice of, it depends on the choice of what you have picked so far. So, I will try all possible subsets. So, for all subsets and I, this is basically, this is my definition, right. I am defining is the optimum number of subsets or sets from S1, S2, Si, okay, let us call this Y, that cover Y, where Y is subset of X and I is, okay, these are the sub problems. Okay, so, but there is some incremental thing that is happening. I am just moving from the end. So, what will be the base case? Suppose I is 1, then what is it? Opt of y comma 1 would be, I want the number of sets 1 always. S1 may or may not cover y, right, otherwise 0. Somehow you want to say that if you cannot cover infinity, you want to put, because it is a minimization problem. So, this would be 1 if y is equal to S1 and infinity otherwise. Basically, I am telling you that I can't cover your set y with S1 alone, because do I really need y equal to S1? If y is contained in S1 is also good, right? Sorry, yeah, because I want S1 to cover y. Y may contain, S1 may contain more things. So, this is the base case. So, base case for every set, for 1 I can compute it. Now, when I go to 2, I have this thing which tells you, right. So, in general, I want to cover my set y with the first I sets. This is equal to minimum of, see if you can cover it with the first I minus 1 sets. You already computed this, because we have computed the smaller guys, or I need ith set. So, it is 1 plus opt of, with the first I minus 1 I do not need to cover y now, y minus Si. Again I have computed it before, because in my table for every smaller I have computed it for every subset. So, in particular y minus Si is also there, I have computed it. So, overall running time, let us compute the number of sub problems. These are the sub problems I am computing. So, how many? 2 power n times m, and time for each problem. Well, this recurrence tells you if you want to compute opt yi, then it is sitting there. It is some two numbers you have to add and find the minimum. So, how much time? Constant time, right? Because there is only exactly two numbers. So, overall run time. So, let me just summarize what we did. So, we have seen a bunch of exact algorithms here. Okay. We were always looking at exact algorithm except for the intermediate time where we were looking at approximation algorithms. But before that, it was all polynomial time algorithms. Now, it is all exponential time algorithms, but in the exponential world, there are different kinds of algorithms. So, we saw for minimum vertex cover, some 1 point something something power n kind of an algorithm. In fact, for 3 sat, we saw 7 power 1 by 3. Okay, this is also some 1 point something power n. For TSP, general TSP, we saw some 2 power n n square, because the brute force here would be like n factorial. And for set cover, the brute force is 2 power m, where m is the size of the family, but we have 2 power n, where n is the size of the universe, 2 power n times m. Okay, so, this is basically the game in the world of exponential time algorithms. I will just mention some famous conjectures which we do not know. So, there is something called strong exponential time hypothesis. So, this, if you recall this 7 power 1 by 3 power n algorithm for 3 sat, how did we get this? We said we look at a clause, there are 3 variables, there are 8 ways of trying them, but instead we will try only 7 and then we recurse. This is all fine if the number of variables in the clause is a constant, but if you do not have any bound on the number of variables, this is a general sat which is also NP complete, then the conjecture is that 2 minus epsilon n algorithm for sat not possible. I mean, this is a conjecture, we do not know that. See, the fact that the problem is NP complete, it only tells you there is no polynomial time algorithm unless p equal to NP. We do not expect a polynomial. But you can ask, okay, but can I get 2 power square root of n algorithm? Can I get 1.3 power n algorithm? And the strong belief, again there is no intuition or anything, there are some work around it, and is that this is called strong exponential time hypothesis. For general sat, you do not expect even 1.9 power n algorithm. I mean, so far we do not know, and this is just a belief again. But there is something called exponential time hypothesis, which is for 3 sat we managed to do it. For 3 sat we did get something better than 2 power n, 2 minus epsilon was possible, but you can ask the question, how far can you go? Can you go down to any 1 plus epsilon? Okay, and that is 2 power little o of n algorithm not possible for 3 sat or any bounded set. Again, this is a conjecture. And these are some rough statements. These are not exact statement of these conjectures, but I am just translating it the way we want. And recently, so if you think about NP-hard reductions, what are they saying? You assume that SAT doesn't have a polynomial time algorithm, and we are trying to show that different problems don't have polynomial time algorithm. But these reductions exactly do that. If this has a polynomial time algorithm, I can use it to give a polynomial time algorithm for the other thing. Similar kind of reductions are known from these conjectures as well. Right? In fact, surprisingly, in the polynomial world, so if you let us say look at shortest path or all pair shortest path, network flows, where you have pretty good n cubed algorithm, n power 4, n square algorithm, you can ask the question, can you improve that running time also? Okay, they are all polynomial, but can you bring it down? And there are some connections. There is a lot of recent research on this work, where if you say that if you improve the algorithm for that shortest path by a bit, then you can solve satisfiability in better than 2 power n. Okay, there are all kinds of such reductions or is really the current area of research in this algorithms world. Yeah, I think that's all I have to say about this. So you saw some sample of approaches, algorithms using dynamic programming in the exponential world, and there are different kinds of exponential functions, and that's also an interesting line of work, where we're not just trying to do polynomial time, but even in the exponential world, take NP-hard problem and see what is the best kind of exponential algorithm you can get. Because there is a recent book about 3-4 years old by Feder Fomin and Dieter Crash. It's called Exact Exponential Algorithm. So there is a lot to be explored in this world as well. Okay. I think I have a lot of time, but I have run out of material to talk, so I'll stop.